Do you see my screen? Okay. So I
Yes.
have spectroscopically decomposed the Birch and the disk component using the 3D spectroscopy from the semi-galaxy survey. This is a schematic diagram showing how to decompose Birch and the disk components. So black line here is an example of the line of sight velocity distribution of a galaxy. If we think this is a combination of a Birch and the disk components, then this black line can be expressed by the flux-weighted sum of two Gaussians. So here we can estimate the shape of the total line of sight velocity distribution from the spectrum from the semi-3D spectroscopy cubes. And also we can estimate the weights of two components from the photometric Birch disk decomposition. So using this information, the penalized pixel feeding method simultaneously estimates the rotation velocity and the velocity dispersion of the Birch and the disk components. So I have decomposed, I succeed in decomposing the Birch and the disk kinematics for 826 semi-galaxies. This is the largest sample for spectroscopic Birch disk decomposition, and also this is the first sample including all morphological types from ellipticals to lace spiders. First, I investigated the distribution of two components in the V over sigma and the lambda R spin parameter. Both V over sigma and the lambda R spin parameter are showing which one is dominant between the random motion and the rotations. Birch and the disk components are well separated in the distribution of the V over sigma and the lambda R parameter. And this is quantitatively saying that Birches and disks are kinematically distinct. Tully-Fisher relation is showing a mass scaling of rotation of late-type galaxies. However, if we plot all types of galaxies in the Tully-Fisher plane, then we find the largest scatter, especially for the early type galaxies, so which are mostly depart from the fiduciary-Tully-Fisher relation for late type galaxies. In the right panel, I decomposed the Birch and the disk rotation, and as you can see, the disk component will follow the fiduciary-Tully-Fisher relation for late type galaxies. Therefore, the Tully-Fisher relation is not an exclusive relation for late type galaxies, but it's a general mass scaling for rotating components of all galaxy types. I did the same analysis for the Faber-Jackson relation. So in the right panel, the right panel shows that the Faber-Jackson relation applies to both Birch and the disk components with the same slope, but with different 0 points. Therefore, the stellar mass also scales the Birch and the disk component, the velocity dispersion of two components for all morphological types. I also investigated the residual trends in the Tully-Fisher and the Faber-Jackson relation. So let's focus on the result for the Birch diffraction. So here, the galaxies show the residual trends in the Faber-Jackson relation with the Birch diffraction. That is, the high B2T galaxies lie on the Faber-Jackson relation. However, low B2T galaxies are apart from the fiduciary-Tully-Fisher, the Faber-Jackson relation. However, the Birch and the disk component have no trend in their residuals with the Birch diffraction or with any other galaxy properties. So therefore, the combination of Birch and disk components generates the residual trends in the galaxy scan relations. So this is the summary. I would like to focus on the finer points that the relative contributions of two components can explain the complex kinematics of galaxies. So if you would like to learn more about my research, then please find my paper from the archive or email me to discuss more. Thank you.
Time out. So questions and answers. There is no questions from the audience yet. So I have a few questions for you, Sri, that when you were talking about these galaxies, at what redshift are these galaxies are?
Yes, SEMI, the galaxy survey targets 3,000 galaxies at the very nearby the universe to the redshift 0.1. So but the peak redshift is 0.03 to 0.04. Yeah.
So you mean to say that you can very clearly distinguish between the disk and the bulge. So you would be able to talk about whether there are spiral galaxies, because normally at high redshift, although they are higher than the redshift you are talking about, the spiral arms are not easily detectable. So your method can probably detect them clearly, right?
Yes, so our samples are mostly in the local universe, so we can clearly separate the bulge and disk component even from the photometrically. So I think, yeah, that is the answer. Yeah.
Okay, there is one question from Stephen. Can you distinguish between pseudo bulges and classical bulges in your models?
Yes, I was trying to find the pseudobulges from my sample. However, we gave the masca, which was the 9.5 solar masses. And we found that most of the pseudobulges they excluded from our sample, and we only find 23 galaxies supposed to have expected to have the pseudobulges. But yeah, so from the current setup, so we cannot discuss with the pseudobulges, but maybe with the better resolution data, we can definitely say about the pseudobulges. Yeah. So mostly our bulge components are classical bulges.
There is another related question from Chris that, so would the pseudobulges look like very similar to disk?
Sorry, would you repeat again?
Bulge. So
Sorry?
there is another question from Chris, which is on the same line, that it seems that they would pseudobulges would count as disk rather than bulge.
Pseudobulges, honestly, we don't have pseudobulges. So we don't know whether they are counted as a bulge or disk, but definitely they would be, even photometrically, they are defined as a bulge. So I think they are counted as bulge component. And one thing I would not like to mention is the bulge component of the late-type galaxies tend to show the rotations. So I think pseudobulges would show the more rotationally supported than the classical bulges.
Okay, Sri, your time is up, and if there are further more questions for Sri, please keep on posting them. We'll get back to her after 12 p.m. Our next speaker is Jesus Gallego, and this is a dissertation talk. So we'll have 15 minutes for him, and he will talk on the Lyman alpha emitters at z equal to 9. Jesus, your time starts now. Please go ahead.
Okay, thank you. I'm sharing my screen. Good morning. This is Jesus Gallego speaking from Universidad Complutense de Madrid, from Spain. I'm going to present the work Deep Near Infrared Narrowband Imaging with the camera Circe at the Gran Telescopio Canarias, searching for Lyman alpha emitters at z equal 9. This is the result of an international collaboration where we have University of Florida collaborators, several people from University of Madrid, and several people from different institutions in Spain. My talk will have the following main sections. I will first address the scientific motivation, then I'll mention about the instrumental setup. I'll focus on the data reduction and development of specific reduction tools for this specific instrumental setup. Then I'll comment on the analysis tools and preliminary results, and I'll finish with a summary and conclusions. Speaking about the scientific motivation, this work is in the framework of the epoch of reionization of the universe. The epoch of the reionization of the cosmic gas after it became essentially neutral is crucial in the galaxy formation process. Unfortunately, many details remain open, so it's still really worth to try to identify high redshift galaxies, try to study them, and try to confirm if they can be qualified as the main sources of reionization or we have to think about different sources. Perhaps the easiest way to select these high redshift galaxies is because they show the Lyman alpha line in emission. In the case of having Lyman alpha in emission, the only thing that has to be done is to detect the emission line, rule out the interlopers, and once the redshift is well measured, you can start analyzing your galaxy. Sorry, I'm going backwards. I'm moving forward, and forward. Okay, our team has been working in the theoretical aspects of the reionization since several years, and we have already published in 2017 what we call AMIGA, which is an analytic model of intergalactic medium and galaxy. It's a paper by Salvador Soler et al. Collaborators in 2017. It's a fully analytic model, and it considers different scenarios for the reionization. In the left panel, you see that there is a possibility of a double reionization scenario. In red color, we see in terms of the redshift, the fraction of the reionization of the universe in the case of a single reionization, and in the right panel, in green color, you see two peaks in the reionization because a double reionization scenario would be possible. The first peak of these two peaks would be at Z about 10, driven by the first generation of stars, the so-called population 3 stars, and the second and definitive peak would be at Z about 6. And this second peak should be due mainly to young galaxies formed at redshift larger than 6. So an observational test for this scenario would be to detect Lyman alpha emitters at redshifts similar or close to 9. So in that case, when we are speaking about a Lyman alpha emitter at Z about 9 or 10, the Lyman alpha emission is redshifted to the near infrared. So our project was based in the narrow band technique, which is a technique that we have used in the past, for example, in 2004, Villar 2008, or Clement in 2012. Using a narrow band filter, you obtain an ultra deep image, and then the target selection, the Lyman alpha emitters are selected because the candidate shows a flux excess in the narrow band filter. This flux excess is due to the presence of the Lyman alpha emission. And it's very easy to identify if the signal is good enough, and you plot all the objects present in the field of view in one of these color magnitude diagrams that we can see, for example, on the right of this slide. Our observational project was based in the use of a near-infrared camera installed at the Gran Telescopio Canarias 10.4 meters telescope. The camera is called Canarias Infrared Camera Experiment, CIRCE. The PI is Steve Hickenberry. It's based on a Hawaii 2RG near-infrared detector, covers the J, H, and K classical near-infrared bands, and it covers a field of view of 3.5 times 3.5 arc minutes. You can see the camera bottom to the left, and you can see one of the raw images obtained with the camera in the bottom to the right. I have to notice here, or it's worth noting, that the cosmetic of the detector is extremely bad. In fact, 2 out of the 32 amplifiers are out of work, and this is why you see these 2 narrow shadows in the vertical direction. In order to optimize the detection of Lyman alpha emitters, our collaboration started a collaboration with the SHOT private company. We defined a narrow band filter with a full width Hall maximum 11 nanometers and centered in the 1.25 microns wavelength. The bandpass transmission should be larger than 90%, and you can see in the left panel, in the blue we have the OH sky emissions, and in the red we have the atmosphere absorptions, the telluric absorptions. The the black dots follow the shape of our filter. Considering the SIRSE camera and the physical properties of this narrow filter, the prediction from our Amiga models was that we should detect, going deep enough, we should detect at least 1 to 3 Lyman alpha candidates using this filter. Sorry, I'm going backwards again, forward and forward. For our deep pointing, we selected one of the AAS tiles, one of the HST Hubble Space Telescope tiles in the cosmological field of the extended growth strip. A total of 18 hours total exposure time were invested in this observation. The data reduction was pretty much complex because there were a lot of systematic effects and problems related with the instrument. So it was divided in 3 main steps. The first step would produce a final single image at each different dithering position. The second step would produce a final combined image for each of the observing blocks. And the third and final step would produce a final single combined image as a result of the 18 hours exposure time. You can see here in the panel on the left, one of the original SIRSE ramp images. The behavior is the typical of the near-infrared images. And then in the right, we already see the first results of the first steps of the data reduction. Once the final image was obtained, we were not very happy because we very soon realized that we didn't reach the depth enough. On the left, you can see the comparison between the with 3 HST image of the same field and our near-infrared, supposedly to be the very ultra-deep image. We were able to find only a few objects in common, in fact, 12 galaxies and 4 stars. And from the very beginning, we realized that there were no narrowband candidates without Hubble Space Telescope counterpart. Anyhow, we carried out, we moved forward. We start analyzing, well, we first identify the objects identified in the narrowband image, and we looked for the counterpart in the cosmological catalogs, for example, candles and 3D HST catalogs. These catalogs provided with ancillary data, photometric redshifts, spectroscopic redshifts, spectral energy distributions, and moreover, stellar mass. This is the color magnitude diagram. In red are the stars, in blue are the galaxies. But again, even if we were expecting 1 to 3 Lyman alpha emitters down to AB magnitude 25, we realized that we were reaching only about 22.5 AB magnitude. So no Lyman alpha emitters were identified. Anyhow, based on the ancillary data, we were able to carry out the typical analysis of the galaxies found, just as a pilot study in preparation of future deeper observations. For example, you can see here the redshift histogram, the star formation rate distribution, and the stellar mass of the different samples. The farthest galaxy that we were able to find is at redshift about 1.5. On the left, we can see the UVJ diagram from Williams et al. 2009. And most of the galaxies are qualified as star-forming galaxies, as expected. And on the right, you see the main sequence of the star forming galaxies. I would like to focus my attention in one of a specific target. The one that we qualified at 105 is the green dot on the bottom left corner of the plot, and is the one identified with a red circle on the left. And this is because by itself, it was a very interesting object, being a low mass local dwarf starburst galaxy. We then checked the DEEP2 archive, and we were able to realize that there was already available a Keck spectra. The Keck spectra shows a strong H-alpha emission, and it also shows a weak nitrogen 26584 emission, which qualifies the galaxy as low metallicity. You can see also the Hubble Space Telescope color composite image on the left, which qualifies this target galaxy as an irregular galaxy. So as a summary, I'm presenting here the first results of our deep narrowband observations using the SIRSE camera at the GTC telescope. We have developed a data reduction pipeline for these and similar instruments. It is very unfortunate that we didn't reach the need depth, mainly because of the quality of the detector, because the signal was so low that we were always living in the readout noise regime of the detector. Because on top of that, the narrowband filter is really narrow. Anyhow, we have developed all the analysis tools, so we are ready for more observations, and we are already working in a new project where we are going to move our narrowband filter, which was designed and produced specifically for this specific redshift, about 9.3, and we are going to move the filter to a new near-infrared camera. Thank you very much. That's all.
Thanks, Jesus. Question and answer time for Jesus, and I do not see any questions yet from the audience, but I have few. So, Jesus, when you were talking about, you were just showing one sample of yours where that had a very low star formation rate, it seems, right? So what are the typical star formation rates for other samples of yours which you have observed these Lyman alpha emitters at?
Well, typical star formation rates have a large range of values, starting at 0.0 something for dwarf galaxies. They could go as high as several hundred solar masses per year for bright galaxies. So there is a huge range. The expected for this kind of objects, the best reference could be the Z about 8.8 galaxy detected by Citrin at collaborators in 2015, and the value could be a few solar masses per year.
Okay, I guess a few solar masses per year is very typical of our galaxies as well, right? So my question is, like, when you say very low star formation, like your ranges are pretty high, from very low to very high. So it's like, what are the physical reasons for having such low star formation rates to such high star formation rates? Do you think that there are some starburst galaxies which have more star formation rates and rest of them have low star formation rates? Like, can you please just clarify on the physics behind it?
Sure. Well, I think the main reason here is the structural nature of the object. I mean, when we are speaking about dwarf galaxies, we are speaking about 10 to the 8 solar masses galaxy. Mm-hmm. The typical star formation rate for this kind of galaxy is less than 1 solar mass per year. When we are speaking about a Milky Way galaxy with 10 to the 11 solar masses, the star formation rate goes as high as 110 or even 100. The second main reason is the star formation history regime. in the sense that some galaxies are truly starburst and some galaxies show continuous star formation. For truly starburst galaxies, of course, the star formation rate reaches higher values. Let's say 50 solar masses per year, 100 solar masses per year, depends.
Okay, so Smuel has a question for you. Could you remind the reason for the peaks?
Sure.
For the two peaks you have shown.
Yeah, the double ionization scenario is a quite curious one because the two peaks, in this scenario, you have two peaks because each peak is related with a different source of ionization. The first source is related with the population 3 stars, which are very massive and evolve very quickly. So after the population 3 disappears, the ionization of the universe goes a little bit down, reaching about 60% or 70%, and then it comes the first generation of galaxies, which are the ones that finally finish their ionization process.
Okay, so I have another question. Like when you talk about the escape fraction of like escape of ionizing photons by two modes, one you are talking about the very massive stars, which are pop 3 stars, and then you are talking about again at a later redshift when the galaxy formation had happened. But then the question is like, what are the typical? If I talk about the typical average escape fraction, then what's your estimate of the average escape fraction of the Lyman continuum photon and its evolution over redshift?
Excellent questions. I mean, very recent theoretical models. I can think about, for example, CATS and collaborators to 2020, or similar theoretical approaches specify that if regular galaxies are going to be the main source for ionization, their escape fraction have to be larger than 10%, okay? Mm-hmm. If escape fraction larger than 10% is really difficult to identify in any local galaxy. Just those galaxies that are really experiencing strong starburst processes with much of the galaxy involved in the process are good candidates to show escape fractions larger than 10%. I'm thinking, for example, I-Streaky 18.
Jesus, I guess your time is up. We will get back to this discussion after 12 p.m.
I'm finished. That's it. Thank you.
Yeah, thanks, Jesus. Our next speaker is Smuel Bialy, and he is from ITC CFA, Harvard University, and he is going to talk on thermal phases of the ISM and their metallicity evolution. Now, your time starts now, Smuel.
All right, thank you. Can you hear me? Can you see me?
Yep.
Can you see my screen? Not yet, because I didn't share it, sorry. Yeah.
Yes.
You should see it now, right?
Yes, please go ahead.
Okay, thank you. So yeah, I'll be talking about this project that was in collaboration with Emil Sternberg, published in 2019. And basically, if we talk about galaxy evolution and star formation, I think it's a good way to understand that we first have to focus on the interstellar medium, the ISM, where everything begins. The stars form in the interstellar medium, mainly in the neutral part of the interstellar medium. We now know that the interstellar medium, the ISM, is very inhomogeneous. It consists of different phases of different densities and temperatures. Mainly the two phases, the WNM and the CNM, the cold and warm neutral medium, very high contrast of density and temperature from 110 to the 4, and these density of 30 and 0.3 are typical to the interstellar medium of our galaxy. Now in the CNM, in the cold phase, that's where we have formation of molecular clouds, and which are then gravitational collapse from stars. We have star formation, human formation, everything you like. So not only that this is very interesting and curious by its own, that you have these two phases that coexist. Imagine it's 100 Kelvin and 10 to the 4 that coexist at the same interstellar medium, and that's a stable solution, as we'll see. But this also have a very important implication for regulation of star formation, because this produces a very natural self-regulation process. The basic idea is very simple, that if you have some star formation rate and suddenly it increases, this increases the amount of UV radiation, thus creating much more heating. The cold phase, the CNM, then starts to disappear. Then you start losing the phase that forms stars, and star formation goes back down. This is the situation in our galaxy and nearby galaxies. In this talk, I want to ask, what are the thermal phases? What's the thermal structure in the nearby galaxies, in all galaxies across cosmic time? And basically, I'll show this diagram that Jesus already showed before. And for me, the main focus is here down here, where I'll focus on the parameter metallicity, because we know that today we have some metallicity in our galaxy, in the Milky Way and nearby. But as we go back in time, the metallicity typically goes down. Finally goes to zero as you go to the dark ages. So this can serve as a time machine. So if you explore the properties of the interstellar medium as function of metallicity, you actually go back in time. And that's the basic idea of this talk. I'll just briefly introduce the model. What we do is we solve the equations of thermal equilibrium, heating equals cooling, and chemical equilibrium, a different formation and destruction mechanisms of molecules, especially H2. For heating, it's dominated by photoelectric heating from UV radiation and cosmic ray heating, which is important at low metallicity. And cooling is dominated by Lyman alpha cooling and metal cooling from fine structure lines of C+ and O1. H2 cooling and heating becomes important at low metallicity, where you lose these cooling mechanisms from C+ and O1. Once we have the cooling and heating and the chemistry, we solve for thermal equilibrium and chemical equilibrium and get the temperature and density as a function of metallicity. So let me start just with the case of solar metallicity. Solar metallicity, here I show the pressures as a function of density. If the pressure is very low, then you only get the warm phase, the W and M, cooled by Lyman alpha. If it's very high, then you get the cold phase. But there's a narrow range of pressure where you have a multi-phase ISM, cold and warm together at the same pressure and the thermal equilibrium. Interestingly enough, observations of atomic carbon shows that the Milky Way value for the pressure indeed falls within the multi-phase strip. Independently, 21 centimeter observations also support the multi-phase ISM. That's the case for our Milky Way. Now, what happens when we go to low metallicity? Here the axes show the metallicity in the y-axis and the thermal pressure on the x-axis. Here we have the Milky Way point at metallicity of 1. And here are low metallicity galaxies, say high redshift, dwarf galaxies, you name it. And what we find is, first of all, at solar metallicity, as you go from warm and you increase the thermal pressure, you get the multi-phase strip. Here's the Milky Way. And then if the thermal pressure is very high, you get the cold neutral medium, ISM, as we saw before. But if you decrease now the metallicity, there's a non-monotonic interesting trend that we see. First, you see it goes down and to the left. That's when photoelectric heating is important. Then cosmic ray heating becomes dominant, and then multi-phase goes to the right. It means you need a higher thermal pressure to maintain a multi-phase ISM. It's harder to get a multi-phase ISM as you decrease the metallicity. Finally, at very low metallicities, or if you like population 3 characteristics, you cannot have a multi-phase ISM, and here you may expect a different mode for star formation than what we are used to in the Milky Way and nearby galaxies. That's the results for the set. So I'll just summarize with these points. The interstellar medium, the structure of the thermal phases depends on metallicity. By the way, here I showed behavior as function of metallicity, but basically in the paper we also explore as function of UV radiation and cosmic rays, which are very important parameters as well. Low metallicity galaxies like high redshift galaxies and dwarf galaxies may have less efficient star formation per unit gas mass because of this trend that we saw, that it's harder to get a multi-phase strip. And finally, at very extremely low metallicities, there's no multi-phase, and we may expect a very different mode of star formation, maybe very bursty, because we don't have this regulation process that is happening at higher metallicity galaxies. And with this, I'll finish. Thank you.
Yes, your time is up. Until now, we don't have any questions for you, but yes, as usual, I have many questions. I'll start with the first one. That when you are talking about that, okay, when you are coming to the lower and lower metallicities, you have the single phase medium. So what is the typical temperature of that single phase medium?
Yeah, that's a good question. So, oops. So basically what happens is at very low metallicities, H2 cooling and H2 heating becomes more and more important compared to at high metallicity, it's just C plus metal cooling and Lyman alpha. At low metallicity, it's all dominated by H2 cooling and heating, and metals plays no role. And this limit, that's what you see here, the temperature goes from the WNM temperature of about 10 to the 4, and then gradually decreases to about 1000 Kelvin and saturates at about 500 or 1000 Kelvin. And this temperature is not arbitrary. This is just the level, the temperature that's associated with the energy levels of H2 cooling, with the lowest energy level, which is about 500 Kelvin.
Okay, so does it also depend on what kind of galaxies you were looking at, how dense are they, or something like that, or no?
So basically, yeah, basically in this regime, so I'll just show another plot to help answer this question. So here in this plot, I show the same plot, but for different cosmic ray ionization rates. And for different UV intensities. So here you can think this might be the star formation rate. If you like, if you increase the star formation rate, you increase the UV and the cosmic ray ionization rate. So this is low star formation rate, this is high. And this entire phase goes to the right and to the left, this multi-phase strip, because you have more heating, so you have to compensate with more cooling, so you have to increase the thermal pressure. Because if it increases, you have a higher density and then more cooling. That's why this goes to the right as you increase the star formation rate. But at the very low metallicities, and no, this is extremely low. This is 10 to the minus 5. So it might be even not physical, because people talk about this phase of population 3 stars and reaching the ISM very quickly and going up to like values of 10 to the minus 3 or so very quickly. So this phase might be very short, but still for this phase, the temperature is always about around 1000, no matter what, because that's just the basic atomic physics that you cannot change.
Okay, so I think we have one question. First, we'll address that, and then I have anyway a few more questions as well. So this is the question from Dennis, and the question is, could you speak a bit more about future observations and how they might test this model?
Yeah, thank you. So one thing people now do, so that it's very difficult to really observe the multi-phase in its whole glory, let's say. But what people sometimes do, they use 21 centimeter observations in emission and in absorption. If you can do absorption, that's the best, but sometimes you can do absorption also. Let me just find this plot. So sometimes you cannot do absorption, but still when you have 21 centimeter in emission, sometimes people decompose into a narrow component and a wide component. And this gives you a sense of the amount of CNM and WNM, and if there are these phases in the galaxy. That's for extragalactic observations. Then also people use C+, because C+ is the main coolant over most of the metallicity UV cosmic ray range for the CNM. So from this observations of C+, you can estimate what's the cooling rate and what's the amount, and if the ISM is multi-phase or not. So I think it's C+ and 21 centimeter mainly through these ways.
Okay, so I have another question. Like when you have gone into the lower and lower metallicity, do you really assume the saltpeter IMF, or do you think about the top heavy IMF where you have more number of massive stars? If it is more number of massive stars, then wouldn't you expect more number of ionizing photons in the UV, which would probably try to dissociate the H2 molecules? And like,
Mm-hmm.
how do you take into account that?
That's a very good point. And in fact, there is, so in this study, we wanted to isolate the how each of the parameters affect the thermal phases. So we didn't go into detailed modeling of galaxies and how the IMF changed this. This effect that you just mentioned will come into this parameter IUV, which is the intensity of the UV radiation field from 6 to 13.6 eV, which will change with the IMF. So you might expect this parameter to change as you go to lower and lower metallicities.
Mm-hmm.
Another effect is that you have less dust absorption, so you have more UV throughout the galaxy because you're affected by a larger volume of stars in the galaxy. So all this is important, and I think for follow-up theoretical work.
Mm-hmm. Okay, and did you only model the? Did you? I think you guessed. I guess you modeled the H2 formation.
Right,
And
right.
did you also model the CO formation? And can you please talk about, if yes, then can you please talk about the redshift evolution? Because I guess your metallicity is kind of mimicking the redshift. So the redshift
Yeah,
evolution
right.
of the CO formation, like at what redshift, or like below a certain metallicity when CO formation stops and
Right,
you are
right.
being H2.
Right, that's a good point. So CO, first of all, CO in this plane would form in the very high densities, especially at low metallicities. It's very nonlinear because for CO, it's not only that you lose them as you decrease metallicity. Not only you lose the metals, but also you lose the shielding from H2 and self-shielding from CO. So it's very nonlinear. Now, another point that is very important is how the dust to gas ratio scales with metallicity, because now there are evidence that it's nonlinear. If it's nonlinear, and that's what we assume here, then the dust falls very rapidly below metallicity of 0.1, and you expect to not have any CO or any measurable CO whatsoever. So I would say the very important factor is here, I think, how the dust to gas ratio scales with metallicity. If it's nonlinear, then at the point where it starts to be nonlinear, you don't have CO whatsoever.
Okay, so like if we take into account all those factors, although we don't have much knowledge about dust to gas ratio uh, as a function of metallicity or as a function of how its evolution with redshift. So can we have some conclusive answer from your end? Like what
Yeah,
would be the typical redshift or typical, say,
I feel,
metallicity?
yeah, I feel, but I mean, I guess the people here that could elaborate more on this, but my feeling is that as you watch galaxies at higher redshift, you're very strongly biased to non-typical galaxies, because the typical galaxies, I think, they would have a low metallicity and no CO observed, and when you watch galaxies at high redshift, you're biased towards the galaxies with high dust contents and high CO content, which I think would not be typical. So I think here we are very much biased. So
Okay, that makes sense. And I would just like to ask one more question. That's when you are, I think you are talking about two stable phases like WNM and CNM. And there are some observations which show that there have been some amount of mass in the unstable phase as well. So do you account for that? And can you comment something on how much
right,
is the amount of mass you would model and predict for the observation to observe in the unstable phases and its evolution with redshift or metallicities?
Right, that's a good point. Indeed, in our galaxy and nearby, there are evidence for a gas in the unstable phase in between this warm and cold. which is thermally unstable. And the thought is that this is mainly from turbulence that throws gas into this phase, and then it's just a very dynamical process. In this particular model, we do not model this because we do focus on the equilibrium solutions. And this is kind of where the gases tend to go to. Honestly, it depends what you're asking for, but I think for extragalactic observations, we even at a hard point to observe these two phases. So going into more details into the into the entire probability density function of the density and temperature, it's already very difficult. And I think the cold phase is really what's important for star formation. So everything that is not cold, whether it's thermally unstable or warm, if you're interested just in the star formation rate, I'm not sure you should care too much about it. For our observations in our galaxies, in our galaxy, in the Milky Way, it's important because we see it. We see it from the different 21 centimeter observations, for example. But yeah, if you're asking how it will change with these parameters, I think basically you'd get less cold gas and more gas into the unstable and the warm phases as you decrease metallicity or you increase the UV.
Okay, but are you aware of any quantitative studies of that?
I mean, there's studies modeling this at conditions like in the Milky Way, like Sauri from 2014 and Siegfried and others. But for different metallicities, I don't think people focus on this for the reasons I mentioned.
Okay, thanks, Mel.
Thank you.
Talk. We'll just, your time is up. We'll move to our next speaker. Our next speaker is Andrew. Zmuel, can you please mute? Yeah. Our next speaker is Andrew Battisti. He is from Australian National University, and he's going to talk on MagPhase plus photo Z, constraining the physical properties of galaxies with unknown redshifts. Andrew, here you go. Your time starts now. You have 5 minutes.
Thank you. Can everyone see it?
Yep.
All right. Thank you very much. So my name is Andrew Battisti. I'm a postdoc at the Australian National University, and today I'm going to tell you about MagPhase Photo Z, which is a publicly available code for constraining the physical properties of galaxies with unknown redshifts. And the release paper for this code was published late last year. So for those of you who might not be familiar with it, MagPhase is a spectral modeling code for obtaining physical properties of galaxies. It was first developed by Elizabeth D'Acunha in 2008, and it covers the full UV to radio wavelength range and performs self-consistent energy balance to balance dust attenuation and dust emission. And it uses a Bayesian framework to construct marginalized likelihoods for a large range of physical properties. But in its original form, it was required that the redshift be input by the user. And this was something that we sought to allow to become flexible. And that's what led to the development of MagPhase Photo Z. So the motivation behind creating this code was to improve upon the basic picture by which we perform studies of galaxy evolution on photometric data sets. So the standard approach is to first run your photometry through a dedicated photometric redshift code to constrain a best fitting redshift, and then to feed that best fit redshift into a separate code such as MagPhase to constrain the physical properties of galaxies. But of course, in that approach, you're effectively removing or throwing away your photometric redshift uncertainties, and so your physical properties are always underestimated. And so in our new approach, we're essentially doing this as an all-in-one treatment where we can simultaneously constrain the photometric redshift as well as the physical properties in order to provide robust parameter uncertainties. Another notable aspect of the code is that it includes the infrared and radio wavelength regimes, and this allows us to break various degeneracies that can often occur in photometric redshift codes between color and redshifts. And in addition, it's also uniquely suited for dusty galaxies that can be undetected at UV optical wavelengths, because in those cases, you effectively only have the infrared wavelengths to constrain redshifts. And so to test the code, we used a large sample of spectroscopically detected galaxies in the cosmos field, which have a large number of photometric filters available. We separate the sample into two redshift regimes. So there's a low redshift and a high redshift sample. Altogether, it's about 4,000 galaxies. On the right, I show a typical fit for one of the galaxies in the cosmos field. You can see there's an extensive number of filters available. On the bottom is just showing the the probability distribution functions for some of the physical properties that were derived. There are many more, but these are just the few that I show here. And the thing I want to note is if we were instead fitting this galaxy to the best fitting photometric redshift, the probability distribution functions shown here are considerably narrower, implying that you have better constraints on your parameters than you actually do, due to the fact that the photometric redshift isn't known to perfect precision. And so the differences in these uncertainties can be several factors. And this is really important to take into consideration when you're characterizing various galaxy. For example, the star forming main sequence, and characterizing things like scatter in the star forming main sequence, and whether or not those are physically driven or just due to the uncertainties in your properties. And so we tested the code by comparing the photometric redshifts to the spectroscopic redshifts, and that's what's shown in this panel on the right. The top left is just showing some of the metrics that are commonly utilized for photometric redshift testing, but the main takeaway is that we achieve quite high precision, accuracy, and relatively minimal bias, and very low rates of catastrophic failures. And this is mainly due to the fact that we're combining both UV optical and infrared, and this helps break degeneracies that often can occur. But a notable thing is that we are not imposing any tuning of the data to fit these redshifts. This is something that often occurs in dedicated PhotoZ codes, and this is what is allowing us to recover physical properties. And if you're interested in, actually, a notable aspect that came out of this result was that the 2175 angstrom absorption feature leads to a bias in photometric redshifts that had to be accounted for in our models. And if you're interested, there's a paper that was published earlier this year where you can find the details on that. And with that, I just want to wrap up and again say that this is a publicly available code, and it's available on the MagFizz website. You can just Google MagFizz, and this should be the first thing that pops up. We have a user blog, and also if you have any questions, feel free to ask questions now, or you can also email me. Thank you.
Thanks, Andrew. We have a question for you from Jesus. His question is, most of the times we have several photo Z and ACD estimations for a single galaxy. For example, it happens for famous cosmologic fields. What is your advice? Use the average value of different estimations, or just select one and work with it?
That's a great question. Well, so the great thing about this code in particular is that it incorporates the uncertainty that you have in your photometric redshift. And so, for example, I only show this one galaxy, but actually I can show perhaps another example here. This is, if we only use certain bands to fit the data, for example, in particular, if you only use infrared bands, you often arise in, you get what's known as a degeneracy in your redshift solution. And so you can get two peaks, one at low redshift and one at high redshift. And in that case, you also get bimodal distributions in your other physical parameters. And so in that case, it's more likely that you should just not trust the fits for this galaxy, because you simply can't constrain the redshift well enough. But if you have a single peak, then if you have a broader distribution in your photometric redshifts, it correspondingly scales to the larger uncertainties in your derived physical properties.
Okay, so he has another following question. Could you comment about blue galaxies with flat ACDs and strong emission lines?
Oh, so that's another great question. So currently the code does not incorporate emission lines. This is something that is being looked into for future work. And so if there are very strong emission lines that are dominating particular bands, it'll currently just result in relatively poor fits to the photometric data. This is something that perhaps other codes that include emission lines currently are better suited, but in terms of infrared detected galaxies, those tend to be relatively weak in emission lines because they're so dust obscured.
Okay, I have a few questions.
Okay.
If there is no other question. Actually, when you are talking about, mostly when you observed, I guess you observed around 4,000 infrared galaxies, right? If
Yes,
if
yeah.
I'm right.
So they're detected in all optical bands, but also include infrared.
Okay, so mostly you are going to you are observing or trying to model the high Z dusty galaxies, right?
Yes.
So wouldn't you be interested mostly in the band from infrared to UV, not below infrared, say to radio? Do you really need to model to lower wavelengths as low as radio?
So you're referring to detecting out into radio?
Yep.
Yeah. Well, so the radio, because there's a well-known radio infrared correlation, the inclusion of radio, if you have, for example, a well-sampled far infrared peak here, doesn't add very much information. But for example, a lot of new radio facilities are coming online that will surpass existing far infrared data in many fields, and that can provide very strong constraints on the amount of dust or star formation in galaxies because it's an unbiased tracer of star formation, at least the radio continuum appears to be. And so that's basically the main benefit for going out to radio is if you don't have, for example, a well-sampled far infrared peak, that can provide good constraints on what the underlying intrinsic star formation rate is.
Okay, so also I have another question, like you are probably having the photometric redshift, right? So do you think that like can you also have information about spectrometric redshift, and which one do you think is more trustworthy?
Well, of course, if you have a
Photometric
spectroscopic redshift, that is the most ideal situation. It's just that
Yep.
Obtaining spectroscopy for galaxies is very observationally expensive, and so you can dramatically increase your sample size that you can use for studies of galaxy evolution if you just work with photometric data sets. And so it's trying to exploit the full power of these massive photometric data sets that are coming online.
Okay, so Jesus has another question for you. How do you deal with AGN contamination? Do you consider all kind of AGN templates?
Oh, so that's another great question that I didn't have time to address. There is a separate version of MagFizz being developed that incorporates AGN. And currently this version of the PhotoZ code doesn't include AGN. And so we recommend that the users of the code essentially use some sort of like color diagnostic or if available, any type of diagnostic that can be used to identify AGN and then essentially exclude them from the fitting. Although it turns out that the photometric redshift is relatively robust to the presence of AGN, and that's at least for ones that are not infrared dominant, because the shape of the UV optical SEDs often don't change too dramatically, especially the location of the Lyman break feature, unless it's an extremely like bright quasar or something. And so essentially we recommend that we try to be identified in some way prior to performing a fit.
Okay, thanks. If there are no more questions, I would like to thank all our speakers before we go on to the empty session of half an hour starting from now. And if you have any questions for any of the speakers of this session, please just keep on posting them. And we already have one question for Sri from Jesus. We'll get back to that, but before that, I would like to thank all the speakers. Thank you all for great talks. Okay, so I'll get back to Jesus's question to Sri. Sri, are you online?
Yes.
Yeah. So Jesus had one question for you. Did you consider the Sloan sample as reference?
Okay, so basically two-thirds of my sample also have the Sloan observation, but I did not fully understand the question well. So would you explain this question again, Jesus?
Jesus, if possible, you can probably unmute yourself and ask the question yourself, if that's okay.
Oh, sorry, I was already typing the new version of the question. Okay, I'll do it using my voice. Well, my question was related with considering the Sloan Galaxy sample as a reference. Do you understand what I mean?
So reference for, so which
For
one?
your plots, for your analysis in general.
Actually, for the decomposition, we cannot use the Sloan spectroscopy. So basically, the aperture spectra cannot be decomposed into Burge and disk component because we need the spatial information. And also because the aperture spectrum, so both Burge and the disk component, for both Burge and disk component, the net rotation would be 0 for both components. So it's almost impossible to identify or differentiate the kinematics of the two components. So probably I think I cannot use the Sloan, the spectroscopic data to decompose Burge and disk component to be used as a reference. Yes.
Okay, thank you.
Okay. Is there any more question for Sri? I guess no. Then we can go for Jesus. The discussion we're having, we can get back to that discussion. This is, are you online? Can you hear me?
Yes.
Yeah, so we're just having the discussion of Lyman continuum photons of these Lyman alpha emitters, and what's your take on the average estimation of average escape fraction of Lyman continuum photons from these Lyman alpha emitters at high redshift, and their redshift evolution if possible, even if it is over the narrow band. Do you have some sense of how may it evolve?
It's something difficult to answer, but I can mention that the escape fraction for this high redshift galaxy is expected to be larger than 10%. And this is already a very high value. Most or all the galaxies in the local universe show escape fractions much smaller than that. I remember a classic study that estimate the escape fraction for starburst galaxies in the local universe closer to 4% or 5%. Anyhow, there is a couple of studies that are trying to identify local analogs of these Lyman alpha continuum leakers, Lyman alpha emitters at high redshift. And the typical galaxies that are closer to these high redshift galaxies are which we qualify in the local universe as extra metal poor galaxies. I'm speaking about the typical dwarf starburst galaxies like ICE-RICKY 18, Second Burakan Survey galaxies, ICE-RICKY 40, University of Michigan 461, POX 186, the typical dwarf star-forming galaxies, which are showing in the local universe the highest birth strengths, the highest specific star formation rates.
Mhm. So,
These galaxies could show escape fractions larger than 10%.
okay, so you mean to say like typically say 10 plus minus 5%, we can say for all sorts of galaxies and its redshift evolution, it remains more or less the same?
Well, I would say that for high redshift galaxies has to be larger than 10%. And then with redshift evolution, the value goes definitely down to 4% or even less.
Okay, yes, because at high redshift we'll probably have more clumpiness as well to take into account that factor. But yeah, do you have any comment on the clumpiness?
Clumpiness is expected to be high. Again, the local analogs are usually dwarf, irregular, clumpy galaxies, where we see different star-forming knots. I can think, for example, about some galaxies that were qualified 20 years ago as hyperactive, in the sense that they show as many as 20, 40, or even 50 clamps, star-forming knots. Of course, using ground-based data is very difficult to resolve spatially all these clamps, but when you can check HST Hubble Space Telescope images, I remember, for example, NGC 7673. NGC 7673 is a galaxy that shows more than 50 star-forming knots. So yes, I would say definitely clumpy.
Okay, because yeah, we had some models. It's our 2015 paper. We actually modeled the disk galaxies and in terms of different midplane density and scale heights, and said that different range of midplane density and scale heights might mimic different, because when you say clumpy, even the clumps are kind of different disks of densities and midplane densities and scale heights. You can kind of mimic them with that. And with that, we had shown that with a huge range of midplane densities of say 1 to 100 particles per cc and scale heights of say 50 to 500 parsec, we found that actually Lyman continuum photon escape fraction remains almost 10 plus minus 5% over the redshift. And we talked about how the supernova explosions, and if there are multiple supernova explosions, they create these huge kind of super bubbles and super shells, and then how this escape fraction can actually be boosted by the presence of the super bubble shells somewhere when you have optically thin pathways there, the Lyman continuum photons can escape more, and when you have these clumpy supercells, there the Lyman continuum photons get absorbed. So these clumps, we have said that they are kind of mimicking the high Z clumpiness. And we could talk about the escape fraction, and it seems pretty much what you are talking about, that yes, it varies from low to high, but not say below a few percent and not even higher than 20 to 25%. Right?
Anyhow, sorry, are you finished?
Yep.
You finished? Okay. No, just to mention that the James Webb Space Telescope is going to be crucial, because these very high redshift objects, when we observe in the rest frame optical using the Hubble Space Telescope, we are observing the ultraviolet rest frame. So we are observing in the ultraviolet. If we want to know the optical aspect of these very high redshift galaxies, we have to go to observe in the J, H, and K band.
Okay. Okay, that's.
So it's difficult to compare clumpiness in the optical with clumpiness in the UV. That's fine.
Yeah, that's true as well. So we'll look forward to more of your observations in future and see what comments or opinions you have on all these aspects. And if there are no more questions for Jesus, should I move on to Andrew first and then get back to Smuel? Yeah, okay. So Andrew, if you are online, if you can hear me, I cannot find any more questions for Andrew, but if any one of you have, because it's a great kind of tool which you had to kind of model constraining different physical properties. Can you please also talk about the star formation rates as a function of redshift, or what kind of star formation rates could you find for those 4,000 infrared galaxies you observed?
So that's a good question. So we, of course, because we were trying to test the code on infrared detected galaxies, and the depth of the infrared surveys aren't particularly deep compared to existing optical data. They were often more biased towards more strongly star-forming galaxies. I actually didn't examine, for example, the distribution of our galaxies on like the star-forming main sequence, but I believe for the most part they are typical star-forming galaxies, except for perhaps the few very high redshift galaxies that we were detected in infrared beyond redshifts of 3.
Okay.
But the code is designed to be suitable for any typical star from galaxies from low star formation rates to high star formation rates.
Okay. Okay, that's great. Okay, thanks, Andrew, because I don't have any further questions, but if you'd like to convey some, if you have something to convey to the audience, some more important points that they should keep in mind for this code, you can go ahead, and then we'll get back to, probably have a few minutes, and then we'll get back to Smuel.
No, I think I'm happy to leave it there. If people have any questions on using the code in particular, I just want to highlight again that there's a user blog for the code on the MagFizz website, but also I'm very happy to assist by email.
Okay, thanks, Andrew. We'll probably then get back to Smuel, but yes, I guess anyway, we had some empty spot after your talk, and we already had quite intensive discussion on many aspects I mostly had in mind, but if you'd like to talk about anything more and
I can add on the question you asked before about CO.
Yep.
I can add a few words on this. In another paper that from 2015, we actually studied this specific question of like how the CO and other molecules change as you change the metallicity, thinking of, again, high redshift galaxies or dwarf galaxies. I'll just jump to one plot that I wanted to show that answers or addresses your question.
Sure.
So in this plot here, we show different. So basically, we solve the chemical, formation and destruction sequences for different molecules, as function of metallicity and other parameters. And,
can you please share your screen?
Oh yes, sorry. Yes. Yeah. Can you see it now?
Yep. Can you please just like kind of make it full screen?
Yeah. Is it full screen now?
Yep.
Okay. So this is the paper I mentioned from 2015 about different molecules. And the plot I wanted to show, so this is a theoretical work again, where we solve the chemistry as a function of metallicity and other parameters. And in this plot, I show these molecules CO, atomic carbon, oxygen, CHO2, and H2O, as a function of metallicity here in the z-axis, and these are fractional abundances, so how much molecule you have relative to H. And what you can see is when you decrease the metallicity, first of all, the gas is molecular. We assume we're talking here about molecular clouds that are shielded from UV. But then at some point about metallicity of 10 to the minus 2, even though you're shielded from UV cosmic rays, can still destroy H2 very efficiently, and then you're dominated by atomic hydrogen, even when UV is not present.
Ah, okay. That's
So,
interesting.
yeah, so you still have some large amounts of H2 in this case because you're still shielded from the UV. The UV is usually the main source of destruction. But cosmic rays are already very efficient because the metallicity is so low, so H2 formation is not rapid enough. That's for H2. And now for CO, what you can see here is that as you decrease the metallicity, first, very naturally, you decrease the amount of any metals, whether it's CO or COO. But CO is basically a large fraction of the carbon population. So most of the gas is in CO. And that's what we know the situation in the Milky Way and nearby galaxies. But then at some point, there's a transition in this point about 10 to the minus 2. And again, this point depends on what you assume on the dust to gas ratio, what I mentioned before. There's a transition where CO starts falling superlinearly with metallicity, and it falls as Z to the power of 2. At this point, at very low metallicities, you have a transition where the dominant molecule is no longer CO, and OH becomes the dominant molecule in molecular clouds. So maybe observations of OH and H2O can be better for high redshift and low metallicity galaxies to detect the molecular gas rather than CO.
Yeah. So would you like to mention some of the observations which are taking into account both, and probably they're doing a good job because they're also taking into account the OH?
So I think currently, most of the observational work is still focused on CO and maybe atomic carbon. OH has its difficulties because first of all the line separation, the energy levels are more spaced, so you need to have a higher temperature gas to excite the OH. On the other hand, at low metallicities, you might have a higher temperature gas because there's less cooling. So I'm not addressing specifically your question. This is less of my expertise, but what I understand is that this might be a future direction, but not so much used today yet, the observations of these molecules. Although H2O was detected in high redshift galaxies, very high redshift galaxies, the water was detected. But again, the problem is that you're usually biased towards towards high metallicity and dusty galaxies, even if you go to high redshifts. As you go to high redshift, most of the galaxies are low metallicity and low dust, but the little bit of the galaxies that are high metallicity and dust are much more easily observed. So I think you're always biased towards these. So it's very difficult to really observe the typical galaxies at high redshifts.
Okay. Okay, thanks. So from your plot, I think I would probably conclude that a metallicity of 10 to the power minus 2 is sort of the transition point for both H2 and CO.
Yeah, although take into again the point about the dust to gas ratio, this assumes here a linear relation. Now that we know that it might be non-linear below a metallicity of 0.1, there are observations by in Zwicky 18 that was mentioned, and other nearby dwarf galaxies that suggests that below metallicity of 0.2 or 0.1, it becomes very nonlinear and the dust falls very rapidly. If this is the case, then these transition points for H2 and CO will move to that metallicity where the dust falls superlinearly, say 0.1 or so. So it might be much more relevant for a larger population of galaxies then.
Okay, that's great.
Okay.
Okay, thanks, Smuel, and we'll probably get back because I think we have taken questions for all the speakers, but if you have any further questions for any of the speakers, or any of the speakers, like even I am requesting all the speakers as well, if you have questions for each other, please keep on posting. And if any of the speaker has something else to talk, like if you want to convey, you feel that some more important points which you right now you have the time to convey to the audience, please go ahead one by one if you really want. I'll just go with one by one, starting from the first speaker. Sri, do you have anything further to share?
Yeah, maybe I can share one figure from my paper.
Sure, please go ahead.
Yeah, do you see this
Yeah, we
figure?
see your skin. Yes.
Yeah. So I briefly introduced that early type galaxies and the late type galaxies show slightly different kinematic behavior for the Berger components. So in the right figure, so this is the lambda R ellipticity plane. So this is a well-known plane, a well-known figure to differentiate the slow rotators and the fast rotators. So here the red dots are the Berger components and the blue dots are the disk component. And as you can see, for the early type galaxies, for most of the Berger components are below this black solid line, which is the demarcation line for the slow rotators. So the Berger component of early type galaxies are actually the slowly rotating. However, for late type galaxies, their Berger component are more spread over toward the higher values of the lambda R and the higher values of the ellipticity. That means the Berger component for the late type galaxies are more rotationally supported than the Berger component from the early type galaxies. So that is a bit I would like to share. Yeah. Okay.
Okay, thanks, Sri. We would probably go to the next speaker. Jesus, do you have anything to share or convey to the audience?
Thank you.
Okay,
No, thank
thanks. Ismail, do you have anything else to share?
No, I think I already summarized with the CO and the difficulties in observing low metallicity and dusty galaxies. Although I would ask the other speakers if they have to add something about the what are the prospects and how from an observational point of view, how can we better observe low metallicity galaxies? If they have something to say on this, that would be interesting.
Yeah, the observers, do you have anything to say? I would probably ask Jesus or Sri.
This is Jesus speaking.
Yep, please go on.
We are now in a golden age of the observational astronomy with so many telescopes and so many surveys going on. The amount of candidates to metal poor galaxies is increasing continuously. The only problem is that it seems that the mechanisms that enrich the metallicity of the interstellar medium are very efficient. So you have to catch the galaxy just in the right moment in the first few million years before the most massive stars evolve and start injecting metals to the interstellar medium. So it's always a question of, well, it's chance, in fact, to finally identify that galaxy that would be experiencing that burst of formation. It has to be very young, of course.
You mean to catch it? It depends on the metallicity you want to observe, right? If you want to observe very low metallicity, then the chances are very low, and you have to catch it very early. But
that's correct.
What about like intermediate metallicities, say 10 to the -2 or something like this? Is this very? You have to catch it very early, or is it like what's the time span for something like this?
10 to -2, the solar metallicity, that's very low, indeed. That's like, very extreme. That's extreme metal poor. Already.
Yeah. I guess that SWIC 18 is what was it? U10 to the
-. SWIC 18 is 1/50, depending on the specific region of the galaxy. because ISVK18 has two main blobs. One of them is 1/50, and the second one is a little bit, has a metallicity a little bit higher.
And that's the most metal poor galaxy.
Well, it's the classic metal poor, extreme metal poor candidate. Some authors claim that there are a few galaxies now which show lower metallicities than ISVK18. But as usual, it depends on the calibration. It depends on the specific region of the galaxy you are analyzing. It is not the same to obtain a global metallicity for the global galaxy, which is always the scenario for high redshift galaxies, by the way. When you observe spectroscopically a high redshift galaxy, you are always obtaining average values for the whole system. When you analyze a local galaxy, most of the times you are analyzing specific regions of the galaxy. But yes, I would say ISVK18 is still the good reference.
Yeah, but this is local.
That's correct. Completely local.
I guess in terms of redshift, maybe another good a good line of evidence for the decreasing metallicities with increasing redshifts come from damped Lyman alpha systems, right? Where
Good point. That's
these are
correct.
coming from absorption. There they see a quite clear trend of decreasing metallicities towards higher redshifts. But this is another kind of observation.
I remember something that was called the Lilly diagram, where I guess you guys are aware of the famous Madau's diagram, which plots the star formation rate density in terms of the redshift. And it shows a peak at about z=2, and then the average star formation rate density goes to lower values, to the local value. Lilly was the first to plot a similar diagram which shows average metallicity as a function of redshift. And it also shows that average population of star-forming galaxies at different redshifts show lower metallicities for higher redshifts.
Right, right. Yeah, there's also a paper by Violino et al. Yeah, about this.
Okay,
Violino,
guys,
collaborators, for example.
Folks, I'll have to probably stop you both, and that have been really interesting discussion, and we had all very exciting talks and really splendid discussions on all the talks, and yeah, we had nice time together. And I would like to thank all the speakers again, and our time is up. We'll have to just finish the session. Thank you all.
Thank you very much. My pleasure.
Thank you.